sklearn, linear model, multitask elastic net. Description: a linear model that minimizes a regularized loss function. It combines the L1 and L2 penalties in order to learn a sparse solution. This is useful when you have a large number of features and you want to find a model that is both accurate and interpretable. The elastic net penalty is a combination of the L1 and L2 penalties. The L1 penalty encourages sparsity by shrinking the coefficients of unimportant features to zero. The L2 penalty encourages robustness by shrinking the coefficients of highly correlated features toward each other. The multitask elastic net class is a specialized version of the elastic net class that is designed for multitask learning. Multitask learning is a technique where multiple related tasks are learned simultaneously. This can improve the performance of each individual task by sharing information across tasks. Inputs: X the training data, where each row represents a sample and each column represents a feature. Y the target values for the training data. Each row corresponds to a sample and each column represents a different task. Outputs: Core the coefficients of the linear model. This is a 2D array where each row corresponds to a task and each column corresponds to a feature. Intercept the intercept of the linear model. This is a 1D array where each element corresponds to a task. Steps: Initialize the model with the desired hyperparameters, such as the alpha and L1 ratio parameters. Fit the model to the training data using the fit method. Use the predict method to make predictions on new data. Metrics: Mean squared error (MSE), a common metric used to evaluate the performance of regression models. R squared, a statistical measure of how well the regression model fits the data. Mean absolute error (MA), a measure of the average absolute difference between the predicted values and the actual values. Visualization plots: Scatter plot of the predicted values vs the actual values. This can be used to visually assess the accuracy of the model. Residual plot: This can be used to identify any patterns in the residuals that might indicate that the model is not a good fit for the data. Coefficient plot: This can be used to visualize the coefficients of the model and identify which features are most important. Fine-tune parameters: Alpha the strength of the regularization. A higher value of alpha corresponds to stronger regularization. L1 ratio: the ratio of the L1 penalty to the L2 penalty. A higher value of L1 ratio corresponds to a stronger L1 penalty. Uncertainty methods: Confidence intervals can be used to estimate the uncertainty in the model's predictions. Bayesian inference can be used to quantify the uncertainty in the model's parameters. Challenges and fixes: Challenge 1: the model may be too complex and overfit the training data. Sample use case that resulted in Challenge 1: training a multitask elastic net model with a large number of features on a small dataset. Fixes to Challenge 1: use a smaller value of alpha to reduce the strength of the regularization. Increase the size of the training dataset. Challenge 2: the model may be too simple and not capture the underlying relationships in the data. Sample use case that resulted in Challenge 2: training a multitask elastic net model with a small value of alpha on a dataset with a high degree of nonlinearity. Fixes to Challenge 2: use a larger value of alpha to increase the strength of the regularization. Add more features to the model. Challenge 3: the model may not be able to handle data with a high degree of multicollinearity. Sample use case that resulted in Challenge 3: training a multitask elastic net model on a dataset where multiple features are highly correlated. Fixes to Challenge 3: use a smaller value of L1 ratio to reduce the strength of the L1 penalty. Perform feature selection to remove highly correlated features. Challenge 4. The model may be sensitive to the choice of hyperparameters. Sample use case that resulted in challenge 4 trying to tune the alpha and L1 ratio parameters without using cross-validation. Fixes to challenge 4 use cross-validation to find the optimal values for the hyperparameters.